Welcome students to this 32nd session on industrial metallurgy. At the moment we are discussing the binary equilibrium diagrams, and in binary equilibrium diagrams we have started discussions on the type 3 binary alloy systems, which are also eutectics. So in this session initially we'll discuss about the eutectic reaction which is shown by the type 3 binary alloys. I'll do that quickly because we have done this in the last session also. Then we'll talk about the classification of type 3 alloys based on the eutectic reaction. We'll show you the labeled lead tin phase diagram with the three types of or the three categories of alloys that we have on the basis of eutectic reaction. And finally, we'll discuss in this session the equilibrium cooling of a eutectic alloy of the lead tin alloy series. So let's get started. You see, this is the eutectic reaction in journal, and then we have shown the eutectic reaction which specifically happens for a bismuth cadmium alloy system. We have, if we have a liquid solution phase of eutectic composition present during cooling at the eutectic temperature, this liquid transforms to a mixture of two new solid phases, alpha of maximum solid solubility 19.510 and beta again of maximum solid solubility 2.5 lead, called the eutectic mixture. Now, this is again something that we had shown in the last session, that based on the eutectic reaction you have a eutectic alloy which undergoes the eutectic reaction completely. So this eutectic composition for the lead tin systems is 61.9 percentage of tin. And you see, all lead tin alloys which are having more than this percentage of tin uh, are called hypereutectic alloys, and all alloys to the left of this which have less than 61.9% tin in them are called the hypoeutectic alloys. So the same thing has been written over here. Eutectic alloy is an alloy of exactly 6.9% tin remaining lead. Hypoeutectic alloys are lead tin alloys with up to 6.9 percentage of cadmium in them, and hypereutectic alloys are lead tin alloys with in excess of 61.5% of cadmium in them. So in this in this session we'll discuss about the equilibrium cooling of the most metallurgically simple lead tin alloy, and that happens to be the eutectic alloy of this lead tin alloy series. So I have taken this alloy at a very high temperature corresponding to point H, as we have discussed in on earlier occasions now, that when the alloy is present at a temperature higher than the liquidus, it's in a complete molten state and it has got only one phase in it, a liquid solution of lead and tin. And because there is only one phase, the chemical composition of this phase has to be the same as is the chemical composition of the alloy in which it is present. And since this is the only phase, 100% weight of the alloy is because of this phase only. So this phase is 100% by weight available. So then when we start equilibrium cooling, when we start cooling this alloy under strict conditions of equilibrium, that means at very slow rates of cooling, no change is observed in its microstructure till we have reached point B. And point B is something special. It's the eutectic point, and moreover we have reached the eutectic temperature. Moreover, this liquid solution is of eutectic composition. So both the conditions which are required for the eutectic reaction, a liquid phase of eutectic composition and the eutectic temperature, both are available. And according to this reaction, 100% by weight of liquid will convert into 100% by weight of eutectic mixture, and that is what is shown at this point B dash, which is a fraction below the eutectic temperature of 183 degrees centigrade. So if somebody asks you what is the microstructure, see, you cannot show the microstructure exactly at point B, because at point B the reaction is still taking place. And if you exactly talk about point B, there some liquid solution is present and some this phase is growing. So it's better to show microstructure just a fraction above this temperature or just a fraction below this temperature. So when I try to show the microstructure of this eutectic composition lead tin alloy at a temperature slightly below the eutectic temperature, this is how the microstructure looks like. You have now this liquid transformed into alpha and beta. You see alpha, which is lead, is generally slightly gray in color, and this tin is generally of fade white color. So the same colors, I have taken care that the same colors are shown to you, so that you can attach to them in a better way. So you have this alternate lamellas of alpha and beta. So the alpha that you have, just the alpha that you get because of the eutectic reaction, is the alpha containing maximum amount of solute in it, and solute in it is tin. So you'll find that alpha is of 19.5% tin, and this is the saturation level of tin that can be accommodated in lead. And similarly, the beta that you have been able to obtain again is containing the maximum amount of lead that could have gone into tin. uh, Here also you can see. So at point B, as I have written, slightly below point B, and at B dash, the microstructure is shown here. And in other words, you can say that 100% of this microstructure comprises of eutectic alpha and eutectic beta. So 100% microstructure is 100% eutectic mixture. And in that 100% eutectic mixture, about 45% is alpha, another 55% is beta. Now students, in type 2 systems, we used to say that as we move from a temperature slightly below the eutectic temperature down till the room temperature, no change takes place, because these were straight lines. So whenever you used to have a drop in temperature, you again remained at 100% bismuth, 100% cadmium. But now here you have clear cut solvus lines which are showing you that as the temperature goes down, the solid solubility of the solute in alpha as well as in beta comes down. So as you go down, suppose if you are somewhere over here, now the alpha that you have is not of 19% tin. Somewhere over here it is of only now 15% tin. Here beta was here of 2.5% lead, but somewhere over here it's only of 2% or 1.75% lead. So the microstructure that is important for you is the room temperature microstructure. So if you come down to the room temperature after doing equilibrium cooling, and if somebody asks you what type of microstructure is here, microstructure looks largely like what it was at a temperature just below the eutectic temperature. But the difference is that the relative weight of alpha and beta has changed, and that relative weight has changed because alpha is precipitating out of it tin in the form of beta, and beta is precipitating out of it lead in the form of alpha. So as you move from this point to this point, now here your alpha is not of 19.5%, it's of about 8%. So where has that remaining 19.5 minus 8%, where has that 12 point where has that 11.5 percentage of tin gone? That tin was forced out of this alpha solid solution. But mind it, when two solids are miscible in each other in the solid state, and if one has to precipitate out, it does not precipitate out independently, it also pulls along with it the other thing that was mixed with it. So no doubt this 11.5% tin comes out, but also draws along with it some lead also. And this second solid solution that gets formed contains more of tin and less of lead, and this solid solution is nothing that is precipitating out of alpha because of decreased solid solubility of tin in alpha. This second solid solution that is coming out is beta solid solution. So what would happen, students, as the temperature drops from B1 to J, or anything from B1 to any lower temperature, alpha will precipitate out of it excess of tin and some amount of lead, and that would be precipitated out as beta. So as the temperature drops beyond the eutectic temperature, alpha precipitates out of it beta, and beta precipitates out of it alpha. So somewhere over here now you have alpha, rather than of 19.5% tin, of 8% tin. And here at this room temperature, the composition of the beta solid solution is given by L. So now the solid solution composition is not 2.5% lead, rather it's only about 1.5% lead. So solid solubility beta has precipitated about 1% additional lead from it. It was 2.5% at eutectic temperature, and it is now 1.5. So somewhere over here, the structure still remains lamellar, but this widths have changed because the amount of alpha has decreased from 45 to 40, whereas that of beta has increased from 54 to 59. So what I've done deliberately is that these white portions, they which were representing beta, have been shown more wider now. So I hope this equilibrium cooling of a eutectic alloy of the lead tin alloy series is clear to you. Thank you so much for watching, and thanks very much.